Welcome to this afternoon session here. My name is Alex, and I'm a postdoc researcher here at Caltech, and we'll be doing this linear optimization tutorial for you. And so please take your time and sit down. Okay. For this is a 1.5-hour session that's going to involve coding here. And to help you with coding, additionally to our wonderful TAs, we have brought guys who are co-authors of this tutorial. Could you just raise your hands? So there's Vahe, Vlad, Albert, and also, okay, Oleg is somewhere else. So you can feel free to contact them if you have troubles. So you've heard the pretty nice and theoretic introduction to this manifold optimization earlier today with Justin. And to continue with that, we have prepared you very down-to-the-earth sort of hands-on tutorial of this manifold optimization using a really nice Matlab library. So does everybody see the screen here? All right, so let's just get started. But for most of the time, I will be seated here because I will be coding along with you. But just feel free to shout your questions, and I will just start explaining. Okay. So please open the GitHub page here. The one you know from yesterday, our Matlab /tutorials here. We have released this tutorial earlier today. You can try that at home, basically. So it's designed to be entirely self-contained. You don't need to read most of the theory, well, virtually any of the theory. It has a lot of hints, and it has the solution notebook. And actually, there are 3 different notebooks. One of them is auxiliary, and 2 are the actual Euclidean optimization notebooks. So we will be working as yesterday in Colab here. So please open the Colab, and please launch the Euclidean this geometric _ techniques _ ML Euclidean opt for ML task. And you will be looking at this tutorial here. So if you launch that independently without Google Colab, you will be having the index working here. Please note that the notebook contains quite a lot of text. That is to basically get you on board with Euclidean optimization so that you don't have to read the textbook, okay? It contains a lot of references, it contains a lot of information. So let me just start going on. So one thing to get started with optimization would be to basically optimize with the simplest possible problem in machine learning, that is the linear regression. Okay, so if you're doing machine learning, you've got to know linear regression, right? So after you've successfully installed all these dependencies here, we only have like a couple of those: the Matlab library and the SciPy, basically, of a particular version. Let's just zoom in so you can see everything nicely. Is it large enough or is it too large? Should be alright. So all of you know the linear regression here. So this is just a real quick recap about what that is and what kind of optimization problem is behind it. So what we have is a matrix of features denoted X, and the response vector denoted y. So what we would like to do, we would like to find the weights that live in the n-dimensional Euclidean space such that this quantity, the mean squared error, will be minimized. You can also note that what is written here is not really a mean squared error, but rather a residual sum of squares. Everybody knows that the commonly computed least square solution has the form, well, this form. This is the pseudo-inverse of the matrix, and you basically multiply it with y. With subtleties, that yields you the least square solution to the linear regression. I will just execute this cell because it will do nothing, it's just for future work. But I would like you to view the linear regression as a multidimensional optimization problem. So we're living in the space of n variables without any constraints whatsoever. That's the n-dimensional Euclidean space. So I guess that everybody knows how to work in this space in terms of taking the derivatives, taking the gradients, taking the Hessians, and so on and forth. And if we just view the linear regression as an optimization problem, we'll typically use gradient descent and formulate some kind of an objective. That is, this residual sum of the mean squared error will be our objective that we will view as a function of the weight W. To find the optimal weights, we will need to find the minimum of this objective. And what we will do is we will just use these very well-known gradient descent that I think that everybody is aware of. We will initialize the weight somehow, find a way of computing the gradient of this quality measure L with respect to W, and we will iterate, well, do the descent, as Justin said, where gamma is the step size. The gradient could be computed analytically and is equal to this 2 over L x transposed y minus x W. So we have pre-coded the solution for you. This is actually the compute gradient method that computes you the gradient vector for the W for the multivariate linear regression, okay? And there's the actual gradient descent here. It's not going to execute anything, okay? So from the lecture, let me just proceed further and you'll soon understand what I'm talking about. So let's proceed further with this man-opt package for Riemannian optimization. So I think Justin has been mentioning that for you, but let us just quickly reiterate. As you have seen, there are analytic ways and there are numerical ways of computing the projections, the retractions, and all the numerics underneath the Riemannian optimization here. And it turns out there are a bunch of libraries that would help you do this. So the Matlab Library man-opt, standing obviously for manifold optimization, and its corresponding version PyManopt are basically the toolboxes that you could use to optimize on manifolds. So they're basically built around separation of manifolds, solvers, and the coasts. So you can define a manifold that you're working on, for instance, the Euclidean manifold that we will do just now. You can define any kind of solver you want, for instance, steepest descent, or the trust regions, or conjugate region, gradient, and so on and forth. And you can define the coast that you're optimizing, for instance, this mean squared error that we were talking about. Okay? So that's about the quickest possible introduction into the PyManopt that one could give. So let us just get familiar with how to do this in code, because this is a very hands-on tutorial. You don't need to know any of the math really behind the Riemann optimization here, because PyManOpt will do everything for you. So what do we do when we want to apply PyManOpt for some kind of some task? What we need to do is we need to have a way of having the automatic differentiation. So Autograd package in Python will do that for us, but also Theano, which is no longer supported actually, but still. And TensorFlow backends are built into PyManOpt, so you can use it. You can use TensorFlow, hopefully with GPU acceleration, to optimize over manifolds with PyManOpt. There is actually the PyTorch pull request also, but we'll talk about PyTorch a little bit later. Okay, now we will have to import. I'm not sure why this looks like this, but that's probably because of the collab. So we actually import PyManOpt as opt, PyManOpt.solvers, and PyManOpt.manifolds, which are the three packages that will give us everything we need for PyManOpt. So the second step would be to basically define the manifold of interest. For instance, I've provided this link here, so you can look at the docs of PyManOpt conveniently. But let me just very quickly say that PyManOpt provides a whole lot of predefined manifolds. For instance, to be real quick, those are the classes provided in the docs, which is quite a handful of manifolds, but is of course no match to the original Matlab library, which provides a load of manifolds more. So you can have spheres, symmetric spheres, complex spheres, circles, Stiefel manifolds, Grassmann manifolds, of course, rotation groups or special orthogonal groups, and so on and forth. Positive semi-definite matrices, and so on and forth. You can work with all sorts of data in these two libraries here. So to instantiate, to work with PyManOpt on manifolds, you need to first instantiate the manifold, and yeah, it doesn't typeset right in the collab anyway. So what you need to input is this highlighted text here. You would instantiate the manifold object by calling the Stiefel class constructor here, and we'll do this just shortly. I have also put in the references to the manifolds, what they are. For instance, you can click on this wiki link and understand what is the rotation manifold, well, at least get an idea of that. So this section of this tutorial is just serving as a reference for everything. So once you forget something, go back to this section and you will find out what to do. So third step would be defining the scalar cost. So this cost must be scalar. We will just shortly understand how to define that in practice, but it has two properties. One, it is a scalar function, so it must return a number. It cannot return a vector, a matrix, or anything else. It must be a scalar, at least here in our examples. And then it has the access to all of the variables defined above, wrapped in this NumPy Autograd code. Then you basically instantiate the PyManOpt problem here. Note the verbosity will control how much output you will get. Instantiate the solver. These are some quick references about the solvers. And you basically call the solver.solve. Okay, let's try and do this linear regression with PyManOpt, just straight ahead. So what we do is we import a bunch of PyManOpt objects, and we also input the Autograd NumPy as numpy. Note that people will usually do the import numpy as numpy, and numpy as numpy is non-differentiable, of course. So autograd NumPy is just a thin wrapper around NumPy objects to be differentiable and for the use with PyManopt and other libraries, such libraries. Let's just generate random data. We don't really care about what's the meaning of it. We just want to try out the PyManopt. So I'm generating 200 objects of size 3 with 200 responses here. So your goal here will be to program the linear regression using manifold optimization. Now, of course, everybody understands that this is not real manifold optimization in some sense because we're working with the Euclidean manifold here. But anyway, it's just the start to get a hands on. And I will do this with you, so just to make sure you get everything done here, and then we'll just work in the next exercise on your own. So I will typically put the autograd.numpy here in the cell just to avoid errors because we tend to import numpy as np, and that overrides this import. So we need to program the coast here, okay? So to program the coast, what we'll need is we'll need to return numpy.sum of the squared residuals, right? So there's this numpy.square function that will do the squaring for us. Then there is y minus numpy dot x and w. So as you can see, it's basically the residuals squared, and you basically sum it together. We can also divide it by the len of y, which wouldn't influence the differentiation here. Now we'll have to define a solver here. So solvers live in the solvers package, and you can have a lot of solvers, like the steepest descent, for example, and I will just create the steepest descent solver for you. Let me just scroll a little bit. So also note that this coast function here, it is aware of the existence of this y variable and this x variable here, even though we haven't passed any of the variables. So it sort of has this access to the data defined before. Okay? So we will be working on the Euclidean manifold. So we will have to instantiate this manifold that will control how we do the projections and retractions and everything, all this machinery underneath the Riemannian optimization. So this Euclidean object, it actually accepts a single scalar. Well, it can accept multiple scalars, but in this case, we will need to input the dimensionality of the manifold, which is 3 in this case, because we have created 200 objects of size 3. So that's pretty much it. What we can now do is we can now Shift-Enter and let the PyManopt basically compute us the solution for the problem. Notice the output, so it compiles the coast function, it computes the gradient, and then it iterates using the steepest descent optimizer, and it outputs you the number of the iteration, the value of the coast, which is the mean squared error, and the gradient norm. You will notice that the value of the coast steadily decreases along with the decrease in the gradient norm until it basically converges. So it's handful to check your gradients and so on and forth. So what it basically does, it outputs you 3 numbers, which are the optimal weights for the linear regression here. So the first number is around 0.3, the second 0.21, the second minus 0.1. Why am I remembering that? Is because we still have our handcrafted
gradient descent that proceeds in just about the same way. So it computes the gradient, but only by hand. It has a pre-programmed expression for the gradient that we have obtained by hand analytically, and we have programmed that. So what it does, it also outputs you the same numbers along with the gradient norm. So you can see that it converges to about the same numbers here. And we also have the analytic formula that basically outputs us a precise closed form solution. So you cannot get any better than that. So you can also see that this value here is just precisely the value up above obtained with Riemannian optimization. This means that our gradient descent with an analytic solution is a little bit less precise than the Riemannian optimization based steepest descent optimizer. And this is because it uses a slightly fancier stepping scheme. So our one uses basically the constant learning rate, while the Riemannian optimization one uses the adaptive learning rate. Okay? So that was a warm-up, obviously. So before we get into a real problem, do you have any questions about how did we achieve all this results? So you basically instantiate the manifold, you instantiate the solver, you program the coast, and you let the solver minimize the coast using on the manifold. Okay? Great, awesome, no questions. I assume this is very clear. So let's just get our hands on the learning this shape space of facial landmarks task here. So, sure. Yeah. And it doesn't have any meaning. No meaning. So it's a linear regression over random data. Obviously, the weights are random. It's just an illustration of how. Yeah. Yeah. It's just, garbage in, garbage out. Okay. So what I wanted to do with this learning, with this shape space of facial landmarks, there is a quick reference, but I wanted to look at the figures here, and this is an instance of the so-called active shape model that is really widely used in computer vision here. So you can notice that all these faces have been annotated with 35 the so-called landmarks. So you can see that the tip of the nose and the corners of the nose, as well as the tip of, as well as the lips and the tip of the chin, as well as actually the three corners of an ear, have been annotated. So why do we need that annotation anyway? It's actually widely used in computer vision technologies to aid face detection and facial pose regression and emotion recognition, and such models that are built on statistical analysis of multiple annotated images are really, really useful, and we'll just convince ourselves in that, I believe, shortly. So there is a short reference about this shape models, active shape models included here, so you can basically, once you come home, you can click on the links and read the, I particularly suggest to read this great reference on active shape models that basically contains all the necessary information on the classical active shape model. And also you can have ready-to-use implementations of the shape model. Most of them are in Matlab, but of course there are production libraries such as dlib, which is actually in C++, and it runs at around 1,000 frames per second. So we're going to build a statistical model of these facial landmarks in slightly 30 minutes. So we will first look at the data, how it actually looks like. We will align these annotations, and then we will compute the shape space and explore it. So let me just load the data. Here, the data loaded is actually, the meaning of this data is the x and y coordinates of the annotated key points on each of the 1,000 images. So you can see which key points are exactly annotated as the left eyebrow out and right eyebrow out and eyebrow out and so on and forth. There are 35 of them, and these have been annotated on each of 1,132 images by at least 3 people. So these landmarks are averaged across 3 people. So let's just look at how this looks like. Just eyeball them. So these are the landmarks without the underlying images. This is the function that we'll be using to basically to look at this data. You can call it multiple times to plot subsets of this data. Let me just disable the landmark ID so we could just look at this facial shapes. We have connected these dots. Of course, they are not connected in the data set. They are just independently annotated. But I have connected that so that it basically will resemble some kind of a facial shape. So I think that anybody, because human vision likes finding structure in data, I think that anybody could easily recognize not only that this is a facial shape, but also its viewing angle, its emotion, and whether the... So this is obviously, this one is obviously a wink, right? And this one is obviously rotated so that we are looking from the bottom, and this one is obviously laughing. So it turns out that this shape of facial landmarks, it has strong structure actually, and we're able to instantly recognize emotion and perspective on this shape. So what we will do is we will build a model that models all these variations in shape and viewing angles across 1,000 annotations. So one thing to note is all these landmarks have been annotated on different images with different resolutions, with different viewing angles, and with different rotation angles. And if you just plot them together, you will see that it's basically a mess. So there is no mean shape whatsoever. That's why it makes sense to first align these landmarks. So let's align them to a canonical pose to proceed with building the active shape model here. This will be done in a simple way with a Procrustes analysis. So the Procrustes analysis is basically, there is actually a nice illustration. What it will do is you have 2 shapes, one is the red, the other one is in blue, and you first scale them to same size, then you will shift them to the same average location, and then you will rotate them to have the same orientation, and you will iterate like this until you converge to a mean shape, to a perfectly aligned collection of shapes. So I would like you to actually no, actually let me do 1 minute more. So we'll need a couple of functions. One is the helper function that will standardize the shape for us, subtracting the mean over spatial coordinates and then projecting that to have the norm of 1. And the other one is a large helper function that we'll employ to align the entire collection of shapes. So here we will be working with landmarks that actually have this shape of 1,000 images by 35 landmarks by x and y coordinates. So the first goal for you to think about will be to use this function here to align the two shapes. So you will have to write this default Procrustes function so that you will align the source shape to the target shape. And just to save you a little bit of time, I will do that for you. Let us assume that all these shapes are aligned. So it turns out that the Procrustes function is actually taking in, oh, there's no docstring. Anyway, it takes in these target shape and the source shape, and if you just look at the, oops, sorry. If you just look at the docstring here, oh, it wasn't important. You will see that what it outputs, you, it outputs you the aligned shapes. It accepts one point cloud and another point cloud, and the landmarks are point clouds. So it outputs you a standardized version of data 1, a standardized version of data 2, and the disparity value. So it minimizes for you the disparity value underneath. So if we just use this function, what we'll have to do is we'll have to skip the first argument. We'll have the aligned shape here, and we'll skip the third argument as well. And we'll return to you the aligned shape. It's as simple as that. If we just forget about doing the standardization, we will standardize some. We will compute some mean shape. We will standardize it. That is, move to the origin and divide by its norm, and we'll do the same for a different shape, and we'll try it with the default Procrustes to align it with the mean shape using the default Procrustes. So let's look at what's going to happen if we do this to two shapes. So this front-facing face is the mean face that has been computed over the entire collection of faces. This one, now the mean shape is in gray in the middle figure here. These are two faces overimposed. Superimposed. The distance between the two in the Euclidean space is 0.29. These are the aligned versions. As you could see, the orange shape here, or the yellow shape, it really depends on how the projector is working. The yellow shape here is slightly better aligned. Of course, you cannot obtain a perfect alignment with because of the deformation of the facial shapes, but it still is better aligned. So if you run that thing on the entire collection, it works pretty fast, and you display the result of this alignment, you will instantly see that the aligned distribution, the distribution of landmarks in the aligned shape that is depicted on the left is a very structured point cloud, and you can easily see clusters of landmarks. So how is this achieved actually? And I want you to get your let's do this basically using Riemannian optimization, and you will do that on your own right now. So the first question is, why do we even need to optimize anything by hand here? So the answer is, what is the Procrustes transform? The Procrustes transform is rotation and scaling, because we do all the centering basically before. All you have to do is to rotate the shapes to be better aligned, and then scale them a little bit along each direction so that they're better aligned. So it actually heavily uses this orthogonal Procrustes problem that seeks to minimize this quantity here over a manifold of over a certain manifold. And this manifold might be the manifold of all orthogonal projections, for instance. So your exercise right now would be, and I will give you maybe 10 minutes to do this before we run out of time and start doing that together. Your exercise will be to program the Procrustes transform by hand using the Matlab library and using 3 variants of the alignment here. Yeah. So what we're going to do is we're having these 2 shapes, A here and B here, to be aligned. And what we're trying to find is this transformation, omega, that will minimize, that will be applied to one of the shapes, and that will minimize the distance between the 2 shapes once transformed. So you transform the first shape, for example, and you compute the distance to the second shape, and you optimize over this distance until they are aligned. So you can have variants about, you can have variants of this omega transform. It could be either a projection, it could be a rotation, and it also could be a rotation plus scaling. So I want you to read this exercise and try to do this yourself right now. And I will give you 10 minutes for that. And then we'll do that all together. And feel free to ask questions for clarification. Also note, please, that the functions to be filled are below this problem setting, and they have been partially pre-filled for you. So it will be really easy to complete them. Also note that there are hints here. So you could use Stiefel, rotations, and the product of rotations and Euclidean manifolds. Regarding the solver, it does not make any difference. You can choose whatever solver you want. For instance, stick to the steepest descent for now. uses what? It shouldn't be. Really? The stack trace. Well, it has TensorFlow support built in, I think. So it might import something from TensorFlow, but not actively use it, actually. Wow. Could you look what is there? What's there, please? So, did anybody have success with any of the functions yet? Need more time? Да, должно быть. Okay. Let me just slowly start doing this. Okay. So what I'm gonna do for now is comment out the two functions and only fill in the first one. So the coast is the Euclidean distance between the two shapes, actually. So Euclidean distances are typically done like this. Anti-square of something. Then we are having the mean shape here, and we are having minus shape what was it? Yeah, right, so there's the mean shape that gets inputted into this function. I'm putting it here. And then there's this shape, and I'm putting it here. And we will be doing NP dot between the R and this shape here. So that will be our coast function, and it will not basically change between the three of the methods, well, nearly. So I can also put it here, but I will just need to comment that out. And for the third one, I'm gonna code it by hand. So here, oh, it's a nice Stiefel manifold being here. Okay, and we will have to return the optimal multiplied by the shape. So that's what it looks like. What do? We define the coast that depends on a matrix R from a space of all projection matrices. Yeah. Yeah. So this is A and this is B. Right. So the point with the Procrustes is you have to align all of the shapes to the mean. Then you re-estimate the mean, and then you iterate like this once again. Exactly. We are only writing the alignment between one shape and the mean shape. So as you can imagine, this is not going to be very vectorized or very efficient code, but this is just for illustration, and it will just work, but you can do a little bit more optimization maybe. So let us just try. I did it wrong actually. Yeah, right. So this mean shape is of shape 35 by 2. Then I need to multiply it from a different side here, because shape is 35 by 2 and R is 2 by 2, so I need to multiply it from the right. Still not aligned. Yeah? Sorry? Art. You think so? You mean, right. Exactly, thank you. Right. So, this is, I'm not showing here the alignment of one shape to the mean shape, but rather we will align the entire collection of shapes to the mean shape and re-estimate it. So run the full Procrustes transform on the shape collection, and it will work for some time. And as you can see, it will actually output you the current mean coast value and the mean difference between the mean shapes over the iterations. But as you can see, this is on the order of 10 to the power of plus 3, while, let me show you this, the original Procrustes here was on the order of 10 to the power of 2. That is one order of magnitude lower than what we have done. So this is because the projection matrices are a not very reasonable choice of a manifold. So it will just align you, and the point cloud, apart from being rotated upside down, which is fixable, hopefully, it will output you a fuzzy point, a fuzzier landmark point cloud compared to what you have before. Because there's a minus here. Yeah, well, this is because it has projected in a stupid way to this mean shape. So it can find you whatever projection it thinks is likely. So it has found you upside down projection. So it's possible. However, I hadn't fully debugged that. I mean, in terms of why this was theoretically should be like this. Let us rather, this is a stupid way of doing this anyway, so let us rather resort to the rotation case, and I will do that quickly because we're having money, we're running out of time, and I will manifolds rotation ons 2, and the output is just the same. So thank you, like this. So let us do the same with rotations. So now we are aligning, working in the special orthogonal group of size 2. So in a group of 2D rotations. So additionally to the projection constraint that the scalar product of xtx should be unit matrix, now we are also having a constraint on the determinant of this matrix. And as you can see, the coast value is improved by an order of magnitude, which means that we're doing things correctly. Now, while it optimizes, let us quickly program the third version of the Procrustes transform that also involves scaling along with the rotation. So, how do you implement optimization over multiple manifolds simultaneously? Because as you might imagine, rotation is in SO2, while scaling is in the two-dimensional Euclidean space. So we are kind of working in the Cartesian product of these two manifolds. So it turns out that this Matlab library has the ability to do that as well. And what you will have as input into your code is the tuple of the rotation and scaling. How do you define this tuple? So you will have to instantiate manifold's product, and this manifold product will accept this manifold's rotations like this, and manifolds Euclidean like this. So now we have defined a product of the rotations manifold times the Euclidean manifold, and we'll optimize over the two simultaneously. And to define the transform, I will need to do these. We'll do the mean shape minus np dot of the shape times rt, and you also multiply by s, which is the scaling factor. So this is what you have for this rotation and scaling cost. So all you have all the difference you have is in here. You additionally multiply it by the scale. And of course, when you return it, you will have to modify accordingly, like this. Oops. Sorry, I got used to that. Let us also run. So as you might imagine, we have a slightly better estimate with the rotation here, but also if you optimize over rotations and scales. Okay. Let me just quickly switch to the code for those of you who are, would like to see it. So this is the cost for that. So notice, yeah. You mean? Yeah. Yeah, it is good. So the scale, you mean what does the scale add, right? So the scale doesn't add much, but it just adds you. If you just look at the cost during the optimization, you will see that it's a little bit lower. It's maybe 1% lower. So scaling doesn't add too much. But yeah, you're right. It's you can just go with the rotations here. So this is the correct landmarks with the rotations. And the scaling is of course optimized a little bit slower because we now have 2 times the optimization, or actually maybe even 4 times the optimization to run because we have a Cartesian product. Okay, but either way, let it do its job. Sure. Yeah. We didn't move it to Euclidean 2. So the question is, we were working in the Stiefel manifold of 2x2 matrices, right? But then we just switched to rotations, and then we switched to rotations plus the scale. So the structure of the coast is now different. We are also multiplying the source shape with the scale by the scale factor, which are 2 numbers close to 1, hopefully, that will scale our shape in both directions. So it's a little bit different problem, just slightly. Okay. Now with these aligned landmarks, we have arrived at our final aligned landmarks. Now let's do the PCA and actually learn the shape space. And the goal will be to program the PCA and apply it to dimensionality reduction using Riemann optimization. So this is similar to what Jesse has been talking about during the lecture. We'll have to reshape the landmarks to 1,000 plus objects of size 70. So now this is just a matrix. You can of course do the PCA on from the Scikit-learn library and project to a lower dimensional space, and this is what you will get, and we'll discuss that a little bit later. Let us do the Riemannian optimization based PCA. So this is another problem that I would like you to look at yourself, and I think we have 5 minutes of time to try this. This is actually a very easy exercise to do. So what we would like to have is we would like to have the sorry about this. We would like to find an orthogonal projection M that would minimize the reconstruction error. So what do we do with these? Let me just zoom in so we could just consider it in detail. So this is actually the problem that we're trying to solve. We're having these data X. We would like to project them using this kind of transformation onto a lower dimensional space, say a two-dimensional space. Then we would like to reconstruct it back and obtain some kind of an approximation from a lower dimensional space to a higher dimensional original space. And then we would like to compute the deviation between the original data X here and the reconstructed omega transposed X. We will seek for an orthogonal projection matrix omega that will minimize the squared reconstruction error. So this projection matrix is all, of course, living on the manifold of all projection matrices. That is the Stiefel manifold from D to R, where D is the original dimensionality of the problem, that is 70, and R is the compressed dimensionality, that is the target number of dimensions that we're compressing to, that is well, 2, or in our case it's the 2. So this part of code actually has all the required information in order to find this low dimensional subspace. So let us just program the PCA by finding this projection from 70-dimensional to 2-dimensional subspace using Pymanopt, and I will give you 5 minutes to do this. It's really quick. You can just program this, it's really easy. You can just program this function by computing the reconstruction error. You define the Stiefel manifold, and then you just solve it. Try to do this now. Sure. Yeah, you can try with less components, but yeah, but why? It does make sense. Yeah, I should project on the line, but it's actually, it means that we'll find you one parameter that will parameterize each shape, one parameter for each shape. So there will be some manifold that you are moving along. No, it's a different. It's just to compare with the Scikit-learn PCA in the end. Yeah, this one is 2. Yeah. No. Okay. So the scikit-learn version was just for the illustration about how you could go traditionally, but here we will go with the Riemannian optimization and find this orthogonal projection matrix. Yeah. So because we're not having enough time, I just try to just speed it up a little bit and program actually the cost function for you, and the rest you have in a hint. So the cost function goes like this. You would do the sum squared, which is the sum of the square, obviously, and then you use the aligned landmarks data to decompose it into a PCA. So what do you do with this? So you multiply the aligned landmarks, which is 70 features, by a 70 to 2 matrix W. So this W is working on a 70-dimensional feature space to project it to a 2-dimensional feature space. Then you restore this 2-dimensional representation back to 70-dimensional representation, and you compare this result with the original aligned landmarks. So if you just and you optimize it on a Stiefel manifold of of orthogonal projection matrices from 70 to 2, okay, then you will find some, this is done with trust regions solver, but it doesn't matter. Trust regions is just the Newton optimization, so it involves Hessian. So we have found some matrix, and if you visualize the reconstructions, you will see something like this. So how do we interpret what we have got, what we've gotten? Yeah. So look at this point cloud of reconstructed landmarks, they are just parameterized by two numbers for each shape. As you can see, we're actually only having the variation from left to right and from up to down. So the maximum variation in the space of facial landmarks is this rotation of facial shape from left to right. And you can easily see that if we explore the lower dimensional linear manifold that is parameterizing these landmarks. So we have pre-programmed, this is actually the next exercise. So is everything all right with everybody about the PCA? Did everybody go okay with this? Has everybody succeeded in computing the matrix? Right? Yeah? Or what? Was it okay? So you got it computed, okay. So let us just visualize this manifold in some reason. Sorry, in some sense. So there is a next exercise that will allow you to actually observe what is going on with this manifold. So let us vary the first parameter. So I have said that we have found the two-dimensional manifold that parameterizes the shape space. So there's a two-dimensional manifold of faces, essentially, right? So let us vary the first parameter. So these two functions, reconstructions sorted along PC, and the plot variability will actually allow us do this. So let us supply them with aligned landmarks with this W opt that is parameterizing the space, and the first principal component here. So this is just our data that we are working with. This W opt is this Stiefel manifold inhabitor, right? So this is the projection matrix, and we will just look at this first projection, this first component here. So what are we going to see here? So what have I done? I have projected these aligned landmarks onto the two-dimensional space. Now I am sorting all my data along the first dimension of this space. So you will see how this data corresponds to different viewing angles of this shape. Okay, so can everybody see this? If you just scroll it from left to right, you will probably see that the rotation angle, so the viewing angle, it goes like this. So you're first viewing your face from the right side, then it smoothly rotates to the left side. So this is one variable that actually defines this manifold of faces. Okay, you can do the same with the second principal component here, and you will it's not a very beautiful result here, but what it shows, it shows the rotation. Well, it's not very nice, but it's showing sort of the rotation in a different direction. It is typically asserted that this second principal component parameterizes the second angle, so the rotation of face from up to down. So it's supposed to be like this, but perhaps this data doesn't have enough variability, so it kind of captures some of the variability here. So I will skip this vary on manifold here, although it is very, very simple to do this your own. So I will just skip it and we'll do the fancy stuff. We will compute the embedding of the spatial shapes in. This is done via multidimensional scaling. So what is multidimensional scaling? You were told by Justin yesterday. So this is an embedding of this n-dimensional space into two-dimensional space. For instance, into two-dimensional space, into a lower dimensional space, of course, that actually tries to preserve distances between the 2 points. So if the 2 points were close in the original space, they will be close in the two-dimensionals, in the two-dimensional or the lower dimensional space. So how do we do this? We actually apply also a projection matrix that is again some matrix living on the Stiefel manifold to this data of ours, and then we end up with a lower dimensional representation. So how do we optimize this kind of a very weird objective here? So it turns out that it's possible to actually directly optimize using Autograd or any automatic differentiation library that you like, such as the TensorFlow. So let us just try and do this and be, sort of rewarded about the result. So we will again work in the 70-dimensional space. So this calculate pairwise distances between points will calculate us the matrix of all pairwise distances between the 1,000 points. So it will be returning us the matrix of 1,000 by 1,000 here. So Euclidean distances is the distance in the original space that we would like to preserve while projecting to a lower dimensional space. Okay? So how do we go about this? So remember that this W is a Stiefel matrix that will project us to a two-dimensional space. So we will compute the projections by multiplying our aligned shapes using this. Then we will compute the calculate pairwise distances between projections. So we will have distances lower dimensional, right? Then we will return NumPy sum of Euclidean distances minus lower dimensional distances squared. Of course. So this is our coast. So as you have, as you see, I have just, I was basically coding it, in a stupid way. So no optimizations, no SciPy, no, performance tunings, whatever. And I will use this manifolds Stiefel 72 manifold here, like this. Let us try, and it's just not solving. Aligned shapes is not defined because it's aligned landmarks, I think, right? Right, it's aligned landmarks. Sorry, I always. So this is the optimization going on here. So it hopefully will find me a nice projection matrix that will actually preserve the distances in the two-dimensional space, and while it optimizes, I will just show you the code so that you could do that yourself as well. So let us wait a little bit, because this is already taking a little bit of time, because we are optimizing over 1 million values here, so the gradients are not very quick. But you can speed it up with TensorFlow and GPUs if you do a little bit of hacking with the AutoDiff in TensorFlow. So it has returned us some matrix here. So let us just project the shapes onto the two-dimensional manifold, and hopefully this amazing thing will display us this embedding. Okay, so I need to zoom out a little bit. So let me just go from, this is our space of embedding. Sorry you couldn't see everything. So every point on this two-dimensional plane is corresponding to one set of facial landmarks, so one annotated shape. The distances between the 2 points reflect the distances in the original space of landmarks. So you can see that as I move my cursor along this longer line, the facial shape will slowly rotate from left to right. Up to some extreme rotations. So this is a profile of a face. Also, the opposite direction reflects viewing the facial shape from above versus viewing it from below. So this internal manifold of faces is also very interpretable in many ways. And if you embed your data set into a higher dimensional manifold that you could still explore interactively, such as the three-dimensional manifold, then you will have more variability. So you can also try to notice increasing degree of emotions, such as the open mouth. So as you can see, all the shapes here have, well, at least most of the shapes here, these are bad annotations, of course. All of the shapes here have actually open mouths, so that they are close together. Okay, so that's pretty much it. There's actually more for you to explore. So this, as I've told before, this IPython notebook and the corresponding collab is actually designed to be self-contained. You can come home and solve all that in silence, and you can also try the second notebook that we won't be able to do right now, that actually yeah, you can also have the solution. So this is another notebook that will do you optimization over a Cartesian product of positive semi-definite matrices. This is already really tricky if you want to go if you want to do this by hand. But PyManopt does all of that for you without having to do, well, virtually anything but the cost function and the choice of manifold. So yeah, so thank you for listening, and I hope you have a great time, you know, hacking all this stuff with TensorFlow, which is I wasn't able to actually do myself. Yeah, thank you.